Hello, welcome to tutorial 2. Today we're going to discuss a preliminary of the most basic models that we're going to learn, which are ARMA processes, right? So we're going to dig in a little bit on what the implication of ARMA processes are, how they can be useful for forecasting purposes. And we are also wanting to like what's behind it and how can we set up a basis for model selection, which is the thing that we're going to focus from next week onwards. All right, so today's I'll like give you a little bit of a warning. Today is going to be a little bit tedious. This particularly question 1 is quite dense. So my recommendation for you guys is to try to follow as I do. I have prepared a slideshow for this, but not trying to like write it on your notebooks, because you're most likely not going to be able to keep up, and that's going to leave you like not wanting to follow me or anything. So just try to be as comfortable as possible. Today is not going to be an easy way, but from next week onwards, hopefully things are going to pick up a little bit. So let's try to make today as easy as possible. So like I was saying, I prepared a slideshow, so let me know if it is shown on your screens, please, just so I know that the screen sharing features of Zoom are working okay. So please, if you can't see my slideshow, just type in the chat and I'll be attentive to it. Anyway, like I was saying, the whole point or the whole objective of our course is to provide forecasting, right? To do forecasts, and one of the strongest, probably the strongest tool that we have for this is the observations that we have from the past, from historic data, right? So that's why time series is so useful, because we have a lot of observations for very few objects, contrary to microeconometric data that will have many different subjects at the same point, and we observe many characteristics. Or in the case of panel data, we have many subjects across a few periods of time, so we can see some evolution, and we observe those variables. But in the work with time series data, we will have a lot of observations, like most of the times hundreds or thousands or tens of thousands of observations of the same subject, which in this case is usually GDP, interest rates, a stock price, I don't know, maybe Bitcoin price, something like that. And we have many observations of them, and we use the previous observations to create forecasts for that variable. So in terms of notation, I just wanted to make this a little bit visible for you guys. So the variable, the variable of interest that we're going to work today, let's call it Y. And we observe it as throughout different points in time, hence the T, the sub-index T that we have here. So that variable YT, it goes by itself. We only observe that particular behavior. So the way we bring past data to our analysis is by using something called lagged values of the variable of interest, right? So we can generate these lagged values, lagged variables, yt minus 1, t minus 2, and 3 minus 3, That way we can bring these variables into a model that will allow us to extract this information and will help us make some inference regarding the future behavior of YT. So if you notice, what we do here is lining the data up with the previous period. For example, one period in the past. So for the period 2, the past observation, one period in the past was, well, that observation in period 1. For example, for period 4, one observation in the past corresponds to this one, 2 observations in the past, so that's second lag corresponds to this one, and 3 periods in the past corresponds to this one. So generating these new columns, these new variables, will allow us to like do this analysis without having to go into like more complex stuff. Okay, so remember, what we're going to do throughout the semester is just learning how to improve our forecasting. That's the most important bit, and the techniques that we're going to learn are going to become more sophisticated. As for this, the techniques that we're going to see first, they're quite like they were the first ones that were invented. So of course they weren't performing particularly good, but they were improved and have gotten to a point where we are actually getting into very interesting results. So for the sake of today's tutorial, we are going to derive a few functions, a few estimations of some statistics regarding this data set. We are interested in checking the expected value, variance, covariance, autocorrelation function, and partial autocorrelation function for the following data generating processes. So we are going to take the most basic model. So that's autoregressive 1, moving average 1, and autoregressive moving average 1. And we're going to see how these processes behave. The goal behind this is that later in the future, when we have, I don't know, we have some observations of a stock price of something, and well, the data in reality is not going to tell us, hey, the best model to model my behavior is an ARMA 2-1, for example. We have to find that out. So the idea today is that we're going to get a basis of how to identify some patterns that when we analyze real life data, we can compare to the patterns that we're going to see today and say, maybe the best model for this would be an AR1, an AR3, whatever. And the way to do that is generating partial autocorrelation functions and autocorrelation functions. I will not be able to answer because you probably will wonder by the end of this tutorial if you will be asked to replicate this. I really don't know. What I can say is that you will probably learn how to do up until this point. For the partial autocorrelation function, I'm just going to mention how it is done, but please don't worry too much about it. So let's start with the first model. That's an autoregressive 1. An autoregressive 1 model. We model YT on a lag value of itself. Of course, the coefficient that this past value will take will be called alpha 1. We have an intersect and an error term. And please remember the condition that a alpha 1 has to be a number in between -1 and 1. So a 0 point something number. It should not be equal to 1, otherwise this model will be problematic. And I will show you the implication of that. So let's start with the autoregressive 1. So for the sake of this exercise, what we are going to do is follow two assumptions regarding the time series that we're going to estimate, to analyze, in this case, YT. We're going to assume, that YT is stationary, meaning that the expected value of YT at every point in time is a constant value that we're going to call mu, okay? I will show you in a second what is the implication of this. Also, we are assuming that the variance of YT at any point in time is also a constant value, and we're going to call it gamma 0, okay? And finally, we assume that the covariance between YT and just thinking, like the covariance between YT at whatever point in time and another point in time, it's also going to be the same, and we're going to call it gamma K. Let me go back to this table to show you a bit better what I mean. If you take this column, you can calculate the variance of this column of YT. It's going to give you gamma 0. We're assuming that if we were to calculate the variance of YT minus 1, it's the same number, gamma 0. If we calculate the variance of this column, YT minus 2, gamma 0, gamma 0. So across all these columns, the variance is going to be the same, and we call that the process variance across all possible t's, t minus 1, 2, 3, whatever. The third condition, the covariance means that you can calculate the covariance between two columns, in this case YT and YT minus 1, and it's going to be a number that we're going to call gamma 1. If you were to calculate that covariance between YT minus 1 and YT minus 2, it's going to be the same. And that number, that gamma 1, represents how far apart the two columns are. For observations or lags of t that are one lag apart, so YT minus 1, or YT minus 1 and YT minus 2, or YT minus 2 and YT minus 3, they are one lag apart, the number is going to be the same, and we are going to name it gamma 1. When they are two lags apart, for example, if you are finding the covariance between YT and YT minus 2, or YT minus 1 and YT minus 3, we're going to call it gamma 2. They are two lags apart, and it's constant across. So if we were to find the covariance between YT minus 10 and YT minus 12, it's the same number than YT and YT minus 2, and it's called gamma 2. I hope that that's clear. If not, just let me know. The second assumption that we make is that the residuals, that error term, are white noise. White noise means that the residuals are generated randomly, right? They don't follow any structure. They don't evolve over time, like following any trend. And they are effectively yeah, that they don't have a significant effect on what the behavior might be of YT. The implications of that is that the expected value of the error terms at whatever point is 0, right? The variance of the error term, again, we can have the error term at contemporaneous, so that would be ET, but we can have ET minus 1, ET minus 2, ET minus 3. All of those ETs, the variance of that will be a constant number that we're going to call sigma squared, something that we can actually estimate, right? And this third condition assumes that the errors at two different points in time are not serially correlated. Therefore, the covariance will be equal to 0. And I brought this graph to show you what I mean by this expected value of YT. Oops, sorry. Of how is this condition, like how does it look like? Like you can see how this time series kind of oscillates around a number. It goes down, up, down, up, down, up, blah, 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 blah. And it always seems to come back, like to gravitate towards the same number. In this case, it's 0, right? Regardless of like how low it goes, like it can go very low, and instead of keep going low, it will eventually come back, like not eventually, right? The next period will come back and will recover that loss and will go up and they will come down. And regardless how high it goes, it will always come back. So that's what it means by this. It's not that that YT is a straight line. It means that it will always come back, right? And that number that it will always come back is what we call mu y. I hope that's clear for you guys. Right, so let's start by calculating the expected value of an autoregressive 1 model. An autoregressive 1 model, we have YT as explained by YT minus 1, right? If we were to have autoregressive 2, then we will have another, like, for example, plus alpha 2 YT minus 2, right? And so on. In this case, we only have one because it's easier to follow. So please don't worry about this. Oops, hang on. All right. So the way we're going to do this is to apply an operation called expected value that from a statistic theory, if you already took that course, this should be familiar with you guys. If not, it's just an operation we need to apply to both sides of the equation. So expected value of YT is equal to the expected value of all of this. And this property, this operation has the property of distribution, it's distributive. So we can, like the expected value of an addition of terms is equal to the expected value, like the addition of the expected value of the terms, right? So expected value of this equals expected value of alpha 0 plus expected value of alpha 1 YT plus expected value of ET. And the next step that we do is to take care of the constants. So expected value of a constant is equal to that same constant. The expected value of the multiplication between a constant and a variable is equal to the constant times the expected value of the variable. And we were going to see, well, what does these expected values mean? And you guys remember, we are assuming that the expected value of YT is equal to mu regardless of what t. So mu here will expected value of YT and expected value of YT minus 1 will be equal to mu. And we are also assuming that the expected value of the errors is equal to 0. So this term here will turn to 0. These ones will be now mu. And then I will just rearrange. We don't know what mu is. We want to get mu in terms of stuff that, or in terms of values that we can estimate. So I put mu on the left-hand side of the equation, then do rearrange a little bit of algebra, and we get mu y in terms of alpha 0 and alpha 1, both of which we can actually estimate. One thing here, in this equation of mu is where you can see this condition at work, right? You can see that if alpha 1 is equal to 1, all of these division will be indeterminate, and that will cause our model to be non-stable, and we don't want that. So that's why I don't want any alpha that is remotely close to 1, right? And please remember this equation, mu equals alpha 0 divided by 1 minus alpha 1, because in a couple of slides we're going to need it. Now, the way to calculate variances is a bit more complicated. The variance operator to a situation where we have a couple of variables and they are all adding together is not distributive. It's not the variance of these plus the variance of these plus the variance of these. We have to learn how to do this. The first thing is to take care of the constants. So the variance in here, I'm assuming that x and y are variables, a, v, c are constants. So c is not accompanied by any variable. So the first thing that you do is that you take care of the constant. This plus or minus here is this plus or minus here. So if this were a negative sign would be held here, but the variance of a constant is equal to 0. A variable doesn't change. A constant doesn't change. So all of this will go away anyway. And we are left with the constant terms that are accompanied by variables. So the first thing that you go is to take sorry, let's see if this works. No, is that you take the first term and you grab the coefficient and you square it, and then you multiply that by the variance of the variable, in this case x. And you take the second term, you grab the coefficient and square it, and then you multiply that by the variance of that variable. And then you mixed both of them, you relate both of the variables. So you grab this plus or minus here, and that's the one that comes here. So again, if this were a negative sign would be here. And then you multiply 2 times the coefficients. So 2 times A times B times the covariance between the two variables. So that's the way this rule works. Now let's see it at work. This is the AR1 model. So I'm applying variance of both sides of the equation. I am left here with a constant with a variable and just a variable. So the first thing, like I mentioned, is just to take care of the constant. You take the constant out of there, and this is going to 0 anyway. And we are left with this addition of two variables. So we start with the first term. We grab the coefficient and square it times the variance of that variable plus, well, actually, this is always a plus. So plus the coefficient for the second term, which is a 1, so 1 squared, so that will come, that will come right around here, 1 squared, but that's no problem, times the variance of the variable, and then 2 times the coefficient, so 2 times alpha 1 times 1 times the covariance between the two terms. Okay. Now, from the assumptions that we made, you probably remember that the variance of yt and variance of yt minus 1, they are a constant term that we name gamma 0. So we replace this with gamma 0. Alpha 1 squared is something that we can estimate, sigma squared as well. And this term goes to 0 because, well, the covariance between two variables that are not related is 0, right? So yt minus 1, when you put that in the equation, you notice that et does not appear in the equation, right? Yt minus 1 depends on yt minus 2 and et minus 1. So there is no et here, just et minus 1. Therefore, et does not have an effect on yt minus 1. Therefore, this correlation, this covariance will be equal to 0. So it's always handy to remember what determines sorry, what determines yt minus 1, in this case, t minus 2, yt minus 2, and et minus 1. So et doesn't have an effect. All of this goes to 0. And we can go forward, and now the only thing in this equation that we don't know what it is gamma 0. We want to find out, and we have gamma 0 in terms of stuff that we can actually estimate, sigma squared and alpha 1. So we're good to go. This, we have gotten to the result that we were looking for. Next up, we are finding the covariance function. So remember, the covariance in this case depends on how, it depends on how far apart the logs are. Log terms that are only one log apart, they are considered of order 1. That would be y and yt minus 1, like I have here for this example. It can also be yt minus 1 with yt minus 2. It's going to be the same number, and we already gave them a number, a name, which is gamma 1. Okay, so the way that the covariance is calculated is by, like, the covariance between two random variables or two variables is the expected value of the first variable minus the expected value of that variable times the second variable minus the expected value of that second variable, right? And from the assumptions that we made, you guys probably remember that the expected value, sorry, I always mixed up the two terms, the expected value of yt and yt minus 1 at whatever point in time is the same, and we name that mu, right? So we're left with expected value of yt minus mu, expected value times yt minus 1 minus mu. But we're going to do something, and I don't like to call it a trick, more like an additional condition that we're going to put into the model, and that is that we're going to set alpha 0 to be 0. What is the implication of making alpha 0 equal to 0? Well, you guys remember that mu was determined to be alpha 0 minus 1 minus alpha 1. So if alpha 0 is equal to 0, then mu will be equal to 0. That's the implication of this. Let me go back to my first slide, if I can. That's going to take too long. But you remember the graph that I showed you guys? This one? Oh, too much. Wait. Well, the implication is that we're setting this value to be 0. The takeaway from it is that for the model, so for the purposes of the model, it doesn't really matter what this number is. It most of the times is equal to 0 anyway. But even if it was 100, that doesn't change the dynamic of the variable, right? It will just like it will fluctuate the same. Like these values here will be different, but the dynamic will be the same. So once you run the model, the results are going to be the same anyway. So we can afford to set this mu to be equal to 0. And that's where we're going to do that there. And you're going to notice, let me go back to the slide that I was working on. And we're going to notice that like making those or setting alpha 0 to be equal to 0, therefore we can cancel this mu. It's going to make our lives way easier because we will reach this equivalency. So little disclaimer here, this is not the way that the covariances are calculated. This is just an equivalency that we reach once we set alpha 0 to be equal to 0. Okay, so we can move from one operation to the other. We can move from trying to find the covariance between these two values and making it equal to the expected value of this. And like you probably noticed by now, it's more comfortable to work with expected values than to work with covariances. Calculating covariances, especially with all the these expected operators in here, it's a little bit like it's super complicated. So we are better off just calculating expected values and going through them, and we will be good to go. And this like equivalency can be expanded to the case where we are calculating the covariance between one variable and itself. Statistically, that is equivalent to the variance of the variable, which will be equivalent to the expected value of that variable times itself. So we can conclude that when we have that we have somewhere that the expected value of a variable squared is equivalent to the variance of that variable. Okay, so it's an expansion of that conclusion that we got. All right, so the next step is that we know how yt is explained. We know that yt is equal to alpha 0, but we have set alpha 0 to be 0, plus alpha 1, yt minus 1, plus et. And we're going to multiply that by yt minus 1. So we do that. We take alpha 1 times yt minus 1 plus, yeah, that's, sorry, alpha 1 yt minus 1 times yt minus 1 plus, so plus et yt minus 1, so et times yt minus 1. So let me wipe these marks here. All right. Now, from the properties of the expected values, we can distribute these. So expected value of this plus expected value of this, that's what we have here. Then I kind of did two steps at once. The first is to take the constant out of the operation, and I will be left with alpha 1 times expected value of yt minus 1 times yt minus 1. And from the result that we just got, we know that the covariance of one variable and it's by itself is equal to the variance of that variable. And so this bit will be equal to the variance of yt minus 1. And in this bit, we have to explore if there is a relationship. So is yt minus 1 related to et? Like I mentioned before, it's not, right? Yt minus 1 is explained by yt minus 2 and et minus 1. So this expression will be equal to 0. We don't need to explore terms where there is no correlation. Et minus 1 is not correlated to yt minus 1, not directly correlated at least. So they will be to 0. They will go to 0. And in here, like I mentioned before, this is equal to the variance of yt minus 1. And we know from our assumptions that the variance of yt at every t, so yt minus 1 included, will be gamma 0. So we have now gamma 1, the covariance for the first order. So that's t's of y 1 log apart. We know how gamma 0 is estimated. Therefore, we can estimate gamma 1. Now, the idea behind a covariance function, there is not a way to like get a formula for the function right away. What we do is called a recursive method. It's like we do for the first few points of the function, we observe what the first point of the function is. We observe how the second point of the function is. And by that point, we try to find a pattern. And if we can find a pattern, then we will like make a conclusion on it or a generalization. So let's move forward to variance of order 2. In this case, is yt's that are 2 lags apart. In this case, yt and yt minus 2. But if you were to do it for yt minus 4 and yt minus 6, it will work just as fine, right? So it's a constant term that we called gamma 2. So the way, again, the same way to operate this, and we know that the expected value of yt and yt minus 2 is equal to mu, and we have set alpha 0 to be 0. Therefore, mu will disappear from here. We're left with the same equivalency as before, where the covariance between yt and yt minus 2 is equal to the expected value of yt and yt minus 2. The next step is expanding yt. We know that yt is equal to alpha 1 yt minus 1 plus et, all of that times t minus 2. So we multiply, so expected value of this times this plus this times this, right? And then we distribute the expected value operation. We have a constant here that we take out of the operator, and we are left with the expected value of yt minus 1 times yt minus 2, which is equivalent to the covariance between yt minus 1 and yt minus 2. And in here, same. Expected value of et times yt minus 2 is equivalent to the covariance between et and yt minus 2. Now, is yt minus 2 directly affected by et? It's not. Yt minus 2 is affected by yt minus 3 and et minus 2. Therefore, this covariance, there is no relationship, direct relationship between these two variables, so all of this goes to 0. And from the assumptions, we, like you probably remember, that the covariance of y's at different points in time is equal to a gamma depending on how far apart they are. In this case, they are 1 log apart. Therefore, this covariance will be equal to gamma 1, which is what we have here, right? We know what gamma 1 is. We know we can estimate alpha 1. Actually, yeah, gamma 1 is alpha 1 gamma 0. Therefore, gamma 2 is equal to alpha 1 gamma 1. So this is gamma 1, this is gamma 2. By now, you probably noticed a pattern. The pattern is that for every subsequent order, the covariance function will be alpha 1 k, so the power that order, times gamma 0. Okay? And yeah, so that way we can generalize, and we don't need to do any other orders for that purpose. Now we will use these covariances and variance to generate something called the autocorrelation function. So the autocorrelation function is very useful in the sense that it allows a graphic observation or a graphic visualization of the dynamic of variables, like the dynamic of the, sorry, not variables, dynamic of the variances of the variable, and allows us to scale those covariances by the variance of the process. Allow me to explain. This row 0, don't worry about this, to be honest. We always put it there, but disregard, it will always be equal to 1 because gamma 0 divided by gamma 0 is it's equal to 1. What is interesting is that the first realization of the autocorrelation function by theory is taking that covariance by order 1 and scaling it by the variance of the process. So we're divided by gamma 0. We know that alpha 1, gamma 1 is equal to alpha 1 gamma 0. This divided by this, we're left with alpha 1. So the first value of row 1 is alpha 1. The second value of autocorrelation function is gamma 2 divided by gamma 0. You guys remember this? So again, we cancel here and we are left with this alpha 1 squared. So the autocorrelation function, again, we also try to find out a pattern. And the pattern is that by every further point in the autocorrelation function is just alpha 1 power that point. So the 10th point in the autocorrelation function will be alpha 1 power 10. And this function will look like a geometric decay since alpha 1 cannot be like lower than -1 or higher than 1. This is always going to be a 0 point something number or a negative 0 point something number. And when they are elevated to a higher power, they will become increasingly smaller. So they will look like something like this. It will start at a point, and oops, sorry, nah, this is hopeless. Start there, then it will start decreasing and decreasing and decreasing and decreasing until it will eventually reach 0. And they will not follow a linear decrease, it follows a geometric decrease. So that's what we call a geometric decay, actually, right? So for autoregressive 1 models, this is how the autocorrelation function pattern looks like. This is the goal for today, just pattern recognition. Now, there is also this is not a replaced for the previous tool is a complement to that tool, and it's called partial autocorrelation function. The partial autocorrelation function, it's computing that same scaling of the covariances by the process variance, but it's also taking into the consideration the intermediary lag effects. So all those indirect effects. Allow me to show you why. For example, let's think of the covariance of order 3, right? In that case, we will be analyzing, for example, yt, and let me put it over here, and yt minus 3, right? But we know that yt is explained by yt minus 1, right? So yt minus 1 has an effect on yt. Yt minus 1 at the same time is explained by yt minus 2. So yt minus 2 has an effect, an effect on yt minus 1, which has an effect on yt. And yt minus 2 is explained by yt minus 3. Therefore, there is also an indirect effect, not only on yt minus 3 on yt, but through the intermediate lag terms. So what this PACF function does is that it accounts for those effects of those lags that are in between. This is t minus 1, by the way. It's not very visible there. Okay, hope that's clear. So since that's a more complicated process, that will make this calculation way more complicated. They are calculated using something called the U-Walker equations. I'm just mentioning that they exist. You don't need to worry about them. You don't need to like learn how they work. I'm just going to show you pretty much the results. You will not be asked to do this. So for the first point of the partial autocorrelation function, so this is a 1, 1, not an 11. The first point of the PACF is the same first point as the ACF, which we have found to be equal to alpha 1 for this particular case. For the second point of the partial autocorrelation function, this is this is formula, so I did not derive this. But what we observe, for example, is that rho 1 is equal to alpha 1. Therefore, rho 1 squared is equal to alpha 1 squared, and rho 2 from the previous result is alpha 1 squared. So this minus this will be equal to 0. So the second point of the PACF is a 0. The third point in the partial autocorrelation function, this is actually where the U-Walker equations become like way more complicated, is that you need to do these operations. I expand these sum terms here. But what I really wanted to show you is this phi to 1 is where we account, like in this case, we are doing lags that are terms that are 3 lags apart, right? So we are accounting for the effects of those intermediate lags, in this case 2 and 1, like I mentioned here and here. So these phi terms here, the ones that transfer those indirect effects. This is the way they're calculated, but please do not worry about this at all. It's just to show you like how it works. Sorry, I think, yeah, I missed a bit. The important bit here is that we are left with this nominator here. Rho 3 is alpha 1 cube. Rho 1 is alpha 1. Rho 2 is alpha 1 squared. So rho 1 times rho 2 is alpha 1 cube. So this minus this would be equal to 0. So in general, we notice that from every point further than the second one, so from the second onwards, the partial autocorrelation function goes to 0. So this function looks like it starts, so this would be the graph. It will start at a cutoff point here that we call alpha 1, and then afterwards, it will just be zeros. Okay, again, this is the pattern for a PACF of an autoregressive 1 model. Yeah, so that's the first model. I'm just going to stop here for a second to check on you. How are you doing? Do you want to check something? Please let me know if everything's fine. If I have lost you already, just, you know, thumbs up on the reactions, an okay in the chat. I would appreciate it just to know that we can power through. Again, another thing that I need you guys to remember is that it's okay if you don't feel like you understand anything from today. Remember, these are recorded. I will upload it later. So so you will be like I did this and I put all the steps there so you can sit on your weekend time maybe and try to like replicate the results, try to find the pattern, a way that works with you, and that way like learn how to do this. Okay. So yeah, if everything's fine, just please let me know. Alrighty, now let's do the whole shebang again for now, the moving average model. One. So the moving average model is predicting or modeling values of YT only depending on previous realizations of the error term. And of course, the current values of the error term. To be quite honest with you, I am not completely aware of how this calculation is done. All that I know of this is the computational side of it. But yeah, in theory, that's how the model works. And we're going to explore what the expected value of this mean. So, we applied the expected value operator on both sides of the equation. We distribute the expected value operator, and we take the constant outside the expected value operator. And up until this point, we can find out what is what, right? What is this? What is expected value of YT? What is expected value of this and this? So we go and check the assumptions. We assume that the expected value of YT, regardless of the t, is mu. Therefore, this would be equal to mu. Well, beta 0 doesn't change. And we also assume that the expected value of the errors, regardless of the t, will be equal to 0. Therefore, expected value of ET minus 1 and ET will be equal to 0. And we are left with this solution. The mean of the expected value of YT, mu, it's equal to beta 0. So that intersect in the model. Please remember these few slides in the future when we do the same trick that we did before to set this beta 0 to be 0. That will directly imply that mu is equal to 0, right? We will do that a bit later. Now to calculate the variance, we'll do the same variance operator on both sides of the equation. First thing, take care of the variance of the constant term, and then take care of the variables. So remember, we'll go one by one. The first term, coefficient squared times variance of the variable, plus the second one, coefficient squared, that's a 1, so that's good, times variance of the variable, plus, and this plus is the one that comes in here, 2 times the coefficient, so 2 times beta 1 times 1, times the covariance between the two variables. So covariance of ET minus 1 and ET. And until this, and up to this point, we see again what's what, right? We know that the variance of the errors, regardless of the point in time, are equal to sigma squared, right? And the covariance between errors at two different points of time is equal to 0. So this component here will go to 0. We replace the sigma squares, but of course, we can estimate sigma square and beta 1. We don't know what gamma 0 is, but we can put it in terms of stuff that we can estimate, right? So rearranging here with a bit of algebra will leave us with this result, which is good to go. Now up to the covariance function, we will do the same first with order 1. So that's two terms of y that are 1 log apart, like y and yt and yt minus 1. We do the operation. Expected value of yt and yt minus 1 are equal mu. But once we set beta 0 to be equal to 0, mu turns to 0, so we can get rid of these terms and again get to the nice equivalency that we got from before. And at this point, we're going to expand yt. We know that yt will be this, right? So we're expanding. Now we multiply. So et times yt minus 1 plus beta 1 et minus 1 times yt minus 1. Okay, I'm going to stop here for 1 second because I feel like it would be better if I just do an extra step here. We'll have the expected value of et times yt minus 1 plus beta 1 expected value of et minus 1 times yt minus 1, right? Doing the equivalency, this will be equal or equivalent to the covariance between et and yt minus 1. And this will not, this will be equal to 0, right? Yt minus 1 will be explained by et minus 2 and et minus 1. So et does not have an effect of yt minus 1, so this term will not matter, but yt minus 1 will be affected by et minus 1, right? Because yt minus 1 will be beta 1 et minus 2 et minus 1. So et minus 1 does have an effect there. So we cannot cancel this term. So that's why I went through and expanded yt minus 1 and put it in here. Okay, so that's a bit of a step that I missed. Sorry about it. We already know, like a bit of a spoiler, this will not account for anything. But in here, we still need to multiply all of these and keep and opening this bracket. Again, this will come to 0 eventually. So we'll start by beta 1 et minus 1 times et minus 1. So that's our term here. Plus beta 1 times beta 1. So beta 1 squared times et minus 1 times et minus 2. So we're left with this term in here. We convert to the covariances. We already noticed that this will go to 0. The covariance of one variable on itself, it's equivalent to the variance of that variable. So this would be variance of et minus 1, of course, times beta 1, plus beta 1 squared times the covariance between et minus 1 and et minus 2. But you, did I get the, yeah, sorry, I had to get a little bit ahead. You guys remember that the covariance of error terms at different points in time will be equal to 0. So this goes to 0 and this goes to 0 for what I mentioned before. Yt minus 1 does not have et in any of these terms, so this will disappear. And well, the only thing that we're left with is that we know that the covariance of yt at like different points in time depends on how far apart they are. They are only 1 log apart, so we replace that with gamma 1, and the variance of the error terms regardless of the t is sigma squared. So we can estimate these two, therefore we can estimate what gamma 1 looks like. Now for the second order, we do the same thing. We get to this point. Now remember, this will not account for anything. We replace yt and do like open this bracket. So et times yt minus 2 plus beta 1 et minus 1 times yt minus 2. Just taking care of the constants and the expected value operator. And we do the conversion like to the equivalency, right? Expected value of et times yt minus 2 is equivalent to the covariance between those two variables, and same for et minus 1 and yt minus 2. And in here, we take a second and we evaluate. Is yt minus 2 depending on et or et minus 1? Nope, it depends on et minus 2 and et minus 3. So neither this nor this covariances will be equal to a number different than 0. Therefore, we are left with the conclusion that gamma 2 is equal to 0. And if we keep going and going, we find that for every gamma, gamma higher than gamma 1, so gamma 2, 3, 4, 5 onwards, they will be all equal to 0. With those results, with the variance result and the covariance result, we can get the autocorrelation function. Remember, again, don't worry about this. The first bit, the first point in the autocorrelation function will be gamma 1 divided by gamma 0. We have those results. What I did here is just getting rid of the sigma squares, and we have rho 1 in terms of something we can actually estimate. So that's good. It's some number there. For rho 2 onwards, we'll be replacing gamma 2 and so on. It will be equal to 0. Therefore, rho 2 will be equal to 0. So in general, all future rows further than rho 2 will be equal to 0. So this function will look like, let me do something here, try to see if this works. This function will look like it has a single point, like the first value here, which is rho 1, and then it will just be zeros. So similar to what we observed in the PACF of the auto-regressive model 1, but this is the ACF of a moving average model 1. And when we have something like this, like a single point and then zeros, we call that a cutoff point. It picks at this value and then goes straight to zeros. And then moving to the partial autocorrelation function, again, I'm not going to stop here at this work. Like I mentioned before, like this is the formula from the Walker equation. I just open it up, accounted for the indirect effects using the same formula that we got before, because those come from the Walker equations. And I just worked through it and I got to this result. I tried my best, but it's a bit, like it's a lot complicated. So I would not recommend. And again, I don't think you will be evaluated on this anyway, so don't worry about it. But one thing does come to mind. Let me go to the next slide where everything is nicer. We start at rho 1, then it turns negative, then it turns positive. And this rho, which we know is a number below 1, so 0 point something, first will be squared, then will be cubed. So we notice that these values will not only start decreasing in absolute value, but it will switch signs, right? This is a formula like the generalization that I can come up with, but please, this is not official by all means. So like, don't like take this with a grain of salt. This is the way I think by looking at these 3 points, but it might be anything, you know? So yeah, I might be wrong. So don't worry, don't stress about this. So yeah, it will start at rho 1, right? Then it will become lower in magnitude, but negative at like 511. And then it will become positive again, but at a lower number. So this will be 533. And then it will become negative, lower, positive, lower, negative, until it will eventually reach 0. So it decays geometrically and it oscillates. So it's an oscillatory geometric decay, right? It goes boom, 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 and it will just eventually reach 0. Now to our last case today. I hope you guys aren't doing too bad. I am aware that this is heavy, but if we power through, I think we will. Like again, just take this. The takeaway here is to know how to get your head around expected values and variances, covariances, and autocorrelation functions at most, but not partial autocorrelation functions. So don't worry about it. Okay, now next question, ARMA 1.1. An ARMA 1.1 model explores changes in YT explained by previous values of YT, previous values of the error, and the residuals. And since it's 1.1, we only have one lag of these terms. ARMA can have, for example, 3.3, in this case, we'll have yt minus 1, yt minus 2, and yt minus 3, and we'll have et minus 1, et minus 2, and et minus 3. So the first term here corresponds to the number of y's, the lags of y. The second number here corresponds to the number of lags of et. Okay, let's do this. Let's calculate the expected value. So we put the operator on both sides. We distribute the operation. And until this point, I'm taking constants out. So this beta 1 goes out here. Everything else, this alpha 1 also goes out here. And we evaluate the expected value of a constant is equal to the constant. So that's good. And in here, we check with the assumptions. We are assuming that the expected value of yt at whatever t is mu. So this will be equal to mu. The expected value of the errors, no, not this, sorry. The expected value of the errors regardless of the t will be equal to 0. So both of these terms will go away. We replace mu here. So the only thing that we can't estimate directly is mu. So we need to rearrange, go through a bit of algebra, and we are left with this. Does this look familiar? Yes, it does, because it's the same expected value of an autoregressive 1 mod. Again, you notice why alpha 1 cannot be even remotely close to 1, because all of these will explode. And of course, you will remember that when we set alpha 0 to be 0, that will make mu to be equal to 0, like we're going to do in a bit of in a little bit of time. Next up, we have the variance. So the variance of these, we apply the variance operator to both sides. We take care of the constant first, and then we're left with the rest of the expression. And this, of course, will come to 0 because, sorry, a constant does not vary. So variance is 0. And in here, now you notice that now we have three variables inside the variance bracket. So we need to take care of that accordingly. The way we're going to take care of that, and let me erase those lines because I'm going to need that space. The way we're going to do this is very similar to what we did before. We're going to start with the first term. So coefficient squared times variance of that variable plus second term coefficient squared times variance of that variable plus third term coefficient, which is 1, squared is 1, so that's good, times variance of that variable. Plus, now we take care of the combinations. So the first combination that I'm going to do, it doesn't have to come in this order, is this with this. So 2 times coefficients, so 2 times alpha 1, beta 1, times the covariance between this variable and this variable, yt minus 1 and et minus 1. I mean, we need to be exhaustive with the combinations. The next one would be yt minus 1 with et, right? So it's 2 times the coefficient, so 2 times alpha 1 times 1 times the covariance between yt minus 1 and et, right? And finally, the last pairing will be the second with the third. So 2 times coefficients, 2 times beta 1 times 1, plus covariance between et and et minus 1. And that way we have successfully performed the variance of this variable, of this equation, sorry. Now we need to see what's what, right? Variance of y, whatever y it is, it's equal to gamma 0. So this will be gamma 0. Variance of the errors, regardless of t, is equal to sigma squared. So this is sigma squared, and this is sigma squared. And we are going to see, now in this second term, in this first covariance, or in this first covariance, we notice that et minus 1 does have an effect on yt minus 1, right? Because because yt minus 1 can be, what is it? Is explained by alpha 1 yt minus 2 plus beta 1 et minus 2 plus et minus 1. So et minus 1 does have an effect on yt minus 1. So this covariance will not be equal to 0. We need to explore more into it. But we notice that yt minus 1, oh, I already had it here, sorry. Yt minus 1 does not depend on et, depends on et minus 2 and et minus 1. Therefore, this will go to 0. That's this 0 here. And from the assumptions, you remember that the errors are not serially autocorrelated. So the the covariance of two errors at two different points is equal to 0. Therefore, all of these will go to 0. So we make the replacements. We know variance this is gamma 0. We know the variance of this is sigma squared and sigma squared. And now we need to go and check what's up with this. So what we do now is to expand on the equation for yt minus 1. So yt minus 1 is equal to this. So we're going to multiply all of these terms. So alpha 0 times et minus 1, alpha 1 yt minus 2 times et minus 1, plus beta 1 et minus 2 et minus 1, plus et minus 1 et minus 1. Whew. Now let's see. This term in particular will be equal to alpha 0 times the expected value of the error, but we know that that's equal to 0, so this will go to 0. Let me see if I have it. Yeah, yt minus 2, it's not explained by neither it's not explained by et minus 1, it's explained by t minus 3 and et minus 2. So this second term will become a 0. That's this 0. The third term, we have et minus 2 and et minus 1. This will become covariance between this and this, which is, as you remember from the equations, is equal to 0. So this will go to 0. The variance between one variable and itself, it's equivalent to the variance of that variable. Sorry, the covariance between one variable and itself, it's equivalent to the variance of that variable. And you remember that the variance of et is sigma squared. So this will go sigma squared. And now we put everything in terms of stuff that we know. The only thing that we don't know here is gamma 0. So we put gamma zeros on the left-hand side of the equation and just rearrange the algebra. And we are left with this kind of complex equation. But in terms of stuff that we can estimate sigma squared, we can estimate beta 1, and we can estimate alpha 1. So we're good to go. Let's go to the covariance. This is going to be a little bit more complicated than before. We're going to have to expand a lot. I already skipping through this part. Remember, if we set alpha 0 to be 0, therefore mu will be equal to 0. And so these two operations will be equivalent. We expand yt, right? We know yt is this. We multiply, so this times this here, plus this times this here, plus this times this here. And we check, right? Expected value of yt minus 1 times yt minus 1, it's equivalent to the covariance between yt minus 1 and yt minus 1, which is equal to the variance of yt minus 1. Yt minus 1 is affected by et minus 1. So that covariance will be different than 0, so we need to explore it. But yt minus 1 is not affected by et. Therefore, this term will become this 0. Let's keep going. Now we need to expand. So I'm expanding yt minus 1 in here. And then same 9 yards, we will multiply. So et minus 1 times this. Yeah, here. Plus this times this. That's here. Plus this times this. That's here. Again, we are going to check relationships. yt minus 2, it's not explained by et minus 1, right? It's not here nor here. So this will go to 0. Et minus 1 and et minus 2 are errors at two different points. So the covariance between them will be equal to 0. So this will go away. And the expected value of et minus 1 times itself will be equivalent to the, let me see if I have it, to the variance of et minus 1. And we know from the assumptions that the variance of yt at whatever t is equal to gamma 0. So this is gamma 0. And the variance of et at whatever t is sigma squared. So we replace that. We know what gamma 0 is. So I just put there and rearrange the algebra, and we're left with this way to estimate sigma gamma 1. So that's for the first order. Now let's do it for the second order. I am now like yt's that are 2 logs apart, so yt and yt minus 2. Expanding yt, I got this, same stuff. So that's why I'm kind of speeding up. You know, it's the same process. So it's not worthy of our time to keep going that in a lot of detail. Again, this can be easily replicated, I think. If you have any problems trying to do this process again, please come to consultation and we can work it out. So multiply this times this, plus this times this. So that's here, here, and this times this comes here. Then we go and check, okay, expected value of yt minus 1 and yt minus 2 is equivalent to the covariance between the two. They are 1 log apart, therefore that will be gamma 1. Yt, do I have it? No, I didn't put it. But yt minus 2 depends on yt minus 3, et minus 2, and et minus 3. So neither et minus 1 nor et has an effect on yt minus 2. So boom, boom, they will turn to zeros. And we are left with a way to estimate gamma 2 quite easily. So if you keep doing this, you probably notice here that gamma 2 is equal to alpha 1 times the previous gamma. So for the next one, gamma 3, it will be gamma alpha 1 times gamma 2, and so on. So for any further point in the covariance function, will be alpha 1 times the previous gamma, right? So for gamma 3 will be gamma 2, for gamma 2 will be gamma 1. And that works from gamma 2 onwards, right? Gamma 1 is a different deal as we saw before. Now, to check the autocorrelation function again, don't worry about this. First point in the autocorrelation function, gamma 1 divided by gamma 0. We have all of this here. But what we can do is we can cancel this with this and this with this, and we're left with this way to estimate phi 1. In phi 1, like we have a way to estimate alpha 1 and beta 1, so we can estimate phi 1. From phi 2 onwards, we know that gamma 2 is equal to alpha 1 gamma 1, and we know that gamma 1 divided by gamma 0 is equal to phi 1, right? We have that just here. Therefore, phi 2 is equal to alpha 1 times gamma phi 1. For phi 3, now we have to replace gamma 3, which we know it's alpha 1 gamma 2. And at the same time, we know that gamma 2 is equal to alpha 1 gamma 1. So we multiply the alphas, we get alpha 1 squared. And again, phi 1 divided by gamma 1 divided by gamma 0 is equal to phi 1. So that's the phi 1 here. And you probably notice again a pattern here. For phi 2, it's row 2 is alpha 1, row 1. For phi 3, row 3, shoot, I'm terrible at the Greek alphabet, sorry. Row 3 is equal to alpha 1 squared for row 2. So it's alpha 1 is squared, it is elevated to that following power, and to the previous power. Sorry, so for row 3, it's alpha 1 squared, and it always goes, sorry, this is a 1 here, and always multiplied by row 1. So we can find the pattern for this. Now, how does this look like? This function look like it shows a geometric decay, right? It starts at a point here, which is row 1, and then you will go and multiply row 1 by a number that is a 0 point something. So this multiplication will be a lower number, definitely. And then we are multiplying that by that 0 point something number again. So it's elevating to the second power. So let's keep, this is the worst. It's keep going and down, 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 down until we eventually reach 0. So this is what we call a geometric decay. And if you remember, that's the behavior that we saw before in the autoregressive 1 model. So the ARMA model takes its autocorrelation function from the autoregressive component in the model. Now for the partial autocorrelation function, again, please don't worry about this at all. I did this in my spare time and I got to this very weird equation. There's probably some sequence there, but I couldn't find it for the life of me. But what I noticed is that this number becomes smaller and smaller. So it will also show a decay sometimes, like actually I think a lot of times it will be an oscillating decay. So we will have to see that in practice because I can't get to a result on this. So that's the way the PACF will behave. Again, don't worry about this. You will not be asked to do this process. You can rest assured there. All right, let's move on to the next question. But let me put the questionnaire up for a second. Now for this point, we're given 8 different data generating processes. So just different values for alpha 1, alpha 2, or beta 1, beta 2, and so on. So we're going to see like what the values of the autocorrelation function will be. But again, no, actually, I will stop for a couple of seconds to see if you guys have any questions. So please fire away or let me know if you're doing okay. All right. So now for questions 2 and 3, what I wanted to propose to you guys is to actually do them combined, right? Because what we're going to do in question 2 is to get the values manually. And then in question 3, we're going to see how the graph looks like. So let's calculate the values and check the graph and compare, and get the values and check the graph. And that way we can combine these 2 questions and it's more visible for us. I think that works better, I think. So let's try to do that. Actually, before we actually do this, let's go to R. So the R Studio window must be displayed in here. If it's not, please let me know. Actually, let me, if you want to follow my work, let me share this in Code Share for you guys. Just a second, I'm pasting it in there and sharing the code in the chat for you. So all the code that we're going to use on R today is in that Code Share link. So what we're going to do first is, like this is good practice. This is to clean up everything that we have here. You can run it, or you can click on the broomstick that we have in here. But it's good to that, like when you start fresh, to have empty stuff in here. Now, please go to Blackboard and download the dataset arma.csv. It should have this command separated values file. Please have it in whatever folder you want and set up that folder as your working directory, please. Remember the way to do this, like one way to do this is by going to session, set working directory, choose directory, and then just navigate through until you find that folder that you want to work on and select it. And you will notice that you'll get that setwd command, It's telling you, hey, I changed the working directory, it's all good. And it will also be shown in this little bar here. Just a refresher of what we did, what I mentioned last week. So now for part 3, let's generate ACF and PACF graphs. So the commands are quite straightforward. For the autocorrelation function is ACF. And for the partial autocorrelation function is PACF. We need to select, oh, actually, let me load the data. I haven't loaded the data. Make sure that the header equal true condition and the separation is by comma, otherwise it will upload weird stuff. And then you have a data set called my data of 500 observations of 9 variables. And let's see how the data set looks like actually. We have 9 columns, 8 for the data generating processes, the time series that we're going to estimate. These time series were simulated. So when you, for example, for this first time series, if you model it using an ARMA 1 model and you estimate alpha 1, that alpha 1 would be 0.75. That's what we mean by simulated data. Okay. And same for 2, 3, 4, 5. So they were all simulated to yield these numbers when run the model with this particular specification. So if you take data generating process 1 and model it using ARMA 1.1, the number was going to be different. But if you model using AR1, the alpha 1 would be equal to 0.75. So we're going to do the graphs. So let's do the first. So this is for the data generating process 1. And from the data generating process 2 onwards, I'm going to show you a way to do this using loops. But mainly what you need is a variable. In this case, we're interested in the data generating process 1 variable from the my data dataset. So that's what the $sign means. This column from this dataset or data frame. And main is an option to give a title to the graph. It's just aesthetic. You can like type stuff here. For example, ACF. Oops, sorry. ACF. Oh my goodness. Of data generating process 1, for example, that can be the case. Or you can use call names. So it will grab whatever column name it has for that particular, for this particular column. So data generating process is the second column. That's why I'm selecting the number 2 here. Okay, whatever way that, but the important bit is that you can notice the differences of the graphs. It's not just the same axis and the same title, so you don't know what's what, right? So just to keep this consistent, I will return it to the original state. So let me run line 10, and we get our ACF for the data generating process 1. Here's what I mentioned with main. It captured that column name as the title of the graph. And let's compare to the number. So let me zoom this graph. Might be too big. That's good. And let me jump back to the presentation. So you, from the work that we just did, you guys remember that the first point in the autocorrelation function was equal to alpha 1, in this case 0.75. The second point in the autocorrelation function is alpha 1 squared, which is this, and third point alpha 1 cubed, which is this. So when we see that with the graph, Again, please disregard the first line. The first line is always going to be 1 because row 0 is equal to 1. So this first line, please disregard. And we start from the second line onwards. The second line, 0.75, you can notice how it's kind of close to 0.8, then 0.56, then 0.42, and then it will keep decreasing until we eventually reach 0. Just as an FYI, these blue dotted lines like signal the confidence interval, the 95% confidence interval. So every bar inside these two bands are effectively equal to 0. Don't worry too much about these ones that kind of show up above a level of 0. Once it gets there, and most of the time it stays there, so we can conclude that it will eventually go to 0, like quite fast. Actually, after the fifth lag, it's going to 0. All of these little things here are caused because this is simulated data, so it's always, you know, a little bit of range of error there. It should not be there, but it's fine. If it happens, it's okay. And as an extra, we were only asked to compute the ACF, but as an extra, you remember how the PACF for this particular case were calculated. The first point was alpha 1, which is 0.75, and then it's just zeros. So let's go back to R and do that for the second for line 11, so for the second graph. And you can see here how it starts at 0.7 something, and then it will just sharply goes to 0. So this is a cutoff point, then everything else is in between the 95% confidence interval. So effectively they're equal to 0, just the way that we noticed from the formula. For the second data generating process, it's still an autoregressive one, but the coefficient is now negative. Alpha 1 is now negative. So when that's the case, the numbers are the same, but the signs will be flipped. So it starts at a negative, then positive, then negative, then positive, and so on. And it will become smaller and smaller in absolute value. And the PACF, well, instead of starting at a positive cutoff point, it starts at a negative, and then it goes to 0. So let's see if that is the case. And we're going to do that from using a loop. So why is this? Because we will have to come here and copy paste, and that's oof. And that is just tiring. So every time you have the chance, you can use the for command in R to code a loop to do operations that are repetitive, right? So you don't have to over and over and over again type and do the same thing. So what we're going to do is to set up a variable that's think of this kind of as a I don't know how to describe it. This variable will not affect this by any time, by any means. It can be named whatever. You can call that test, and whatever. Oops. Well, v. Whatever v is, it will be replaced. Whatever v is inside the curly brackets will be replaced with the number that is currently run in the loop. So for the first run of the loop, which starts at 2, all of these v's will be replaced by 2's, right? So we'll have the ACF of the third column of my data, which is DGP2, and using the name of the column for the third column of my data, DGP2. And same for the PACF. At the second run of the loop, all of these are going to turn into 3's. So now we are going to check on DGP3 and so on until DGP8. I hope that's not too too complicated. So we just change this. Again, I will not change it to Y. Whatever you put in here will work just fine. And you delimit the for command by opening a curly bracket and then closing it. And anything in between will be done repetitively for this interval of values of p. Okay, so let's do that. When you run a loop, please run like highlight the whole thing. Do not forget to include the last curly bracket. If you leave it like that, then you get something that's quite annoying, and it's this plus sign. This plus sign will not allow you to do anything until you actually you can press escape and fix that up. So highlight everything, run, and it will make a bunch of graphs. You notice how it jumped straight to the last data generating process. So you can navigate through your plots using these blue arrows here. So let's go to the DGP2 to see what's up there. The DGP2 starts at a negative point, 0.75, then goes to a positive 0.5 something, negative 0.4 something, then it goes to a positive, probably something 0.2, 0.3, then to a negative 0.1, I think, and then it will put a little bit of fight later, but it will eventually just go straight to 0. So it will oscillate and decay when that's the case. When the model is an autoregressive one with a negative coefficient. Now, let's see what happens when alpha 1 is dangerously close to 1, and it's that this decay is not fast at all. It's very slow, right? It goes from 0.95 to 0.90, then to 0.86, and probably to 0.84, and keep decreasing, lower and lower and lower, and it's going to take a long time to reach 0. So that's why when our alphas are estimated to be close to 1, these models will not work. They will not work properly, and most likely that's caused because the time series was not stationary to begin with. So we need to be careful with that. So remember, it starts at 0.95 and will decay very slowly, and the PACF will have a cutoff point at 0.95 and will go to 0 right away. So that's the ACF for the data generating process. Overlap those two things. It will start at 0.95, that's here, 0.90, 0.98, 95, and it will go and decay very slowly until it will eventually reach 0. And now for the PACF, you notice how it starts at 0.95 and then goes straight to 0. So this is actually a pattern that that is a characteristic of not stationary variables, non-stationary time series. So be very careful when you notice such slow decays. That's a bad sign, and that accompanied by a PACF that has a cutoff point very close to 1 and then it goes straight to 0. So again, today is all about pattern recognition, and that pattern is something that we're going to come across quite often, and we need to be careful. Now, the next example is an autoregressive 2 model. So we have yt-1 and yt-2 as explanatory variables for yt, and we have alpha 1 to be 0.5, alpha 2 to be 0.25. Now, we did not work the ACF and PACF functions for an autoregressive 2 model. So I'm just giving you guys the answer. Will be row 1 will be this, row 2 will be this, and row 3 will be this. You're welcome to try that on your own if you want, but the values here will be starting at 0.67, then 0.58, 0.546. So it will also decay from that starting point, but since these values are not close to 1, it will not start super close to 1. And I did not calculate a PACF. It was only asked to do the ACF anyway, so I will not bother. So let's check the ACF for that fourth data generating process. Notice how it starts at above, a bit above 0.6, then it goes to a little bit below 0.6, so that's 0.58. Then a little bit above 0.4, so that's 0.45, and it will keep, not from this. Remember, always disregard the first line, please. Just start from here, and it will decay, until eventually reaches 0. And it doesn't take that long to reach 0. Now let's see how the PACF looks like. It starts at a determinate point. It has 2 cutoff points. You notice that now. And then it's all zeros. So that's another sign, another pattern to be mindful of. When it has 2 autoregressive components, it will have 2 cutoff points in the PACF. If it has 3, then it's likely an AR3. And since they are both positive, then these 2 cutoff points will be both on the positive side. Because our next example happens when one of the coefficients of an AR2 model is negative. So we notice that, again, this is worked on my own, so don't worry about this, but we notice that it starts at 0.17, then it goes to negative 0.46, then negative 4.20, and then positive 0.18. So it oscillates, but it doesn't oscillate like positive, negative, positive, negative. It takes a while. Positive, negative, negative, positive, then it's likely positive again, then negative, and so on. So that happens. That's how it changes the oscillation towards 0 when you have 1 positive and 1 negative value. So let's see that. You see, it starts at a positive, then negative, negative, positive. This is positive a little bit, then it just decays to 0, but it tried, right, to go to a negative after, but it wasn't high enough. So that decay, it's not point, it's positive, negative, negative, positive, positive. So it's a different kind of oscillation. And the partial autocorrelation function will have 2 cutoff points. This is not a decay, right? It's a low number, then a higher, has 2 cutoff points, and then everything else is 0. So this is something, again, to be mindful of. If you don't remember all the patterns, don't worry about it. When we do model selection, we will do this over and over again. So we don't need to worry too much about this. The next model, the next data generating process is an MA1, right? YT explained by a lack of the error and the contemporaneous errors. So let's see how the pattern looks like. You guys remember from the ACF, it starts at row 1, and then it will just go straight to zeros. So it has a cutoff point and then zeros. And the PACF, even if the coefficient is positive, it will start positive, then it will decrease in absolute value, and it will also oscillate, right? Positive, negative, positive again, and likely it's going to be a negative afterwards. So let's see the graphs and let's compare. For the ACF, it starts here at 0.48 and then sharply cuts off to be 0. So we can see that in here. Please, again, disregard the first line. I don't know why this 0 is not the axis. It moves it one step ahead, and it drives me crazy. But don't worry, disregard that. And now the PACF. you can notice how it starts at 0.48, then it will start to decay, oscillating towards 0. The next data generating process is actually an MA2. So now we have two lag values of the errors as regressors for YT. And in this case, we have two alpha, like beta 1 and beta 2, that are different signs. So again, we did not work this out in our tutorial. We did this on a different location, but this is the equations for phi 1, phi 2, and then after phi 3 onwards, it will just go to 0, similar to what we did, to what we saw in the MA1, but in this case, it will cut off after two cutoff points. So number of coefficients there means number of cutoff points in the ACF. And since these signs are inverted, then they will oscillate as well. So let's see that. And this is what I mean. It will go on a positive, then it's a negative, and then it's just straight to 0. It's not a decay, it's just two cutoff points. So two cutoff points in the ACF might indicate two moving average components. And the PACF behaves similar to the moving average one. It's an oscillating decay. It goes up and down, up and down, up and down, until it would eventually reach 0. Now, finally, the last model that we're analyzing is an ARMA 1-1 model. We have YT-1 and ET-1 as regressors of YT. We have only one of those lags each. If you guys remember, we calculated this. Sorry, we have row 1, row 2, row 3 onwards. And yeah, the ARMA model takes the ACF from the autoregressive components. So this will behave just as the AR1 model. It will start decreasing and decreasing geometrically until it reaches 0, like we can see here. Start here at 0.8 something, 0.6 something, 0.4 something, until it reaches 0. Again, don't worry about this. This is probably due to the data being simulated like randomly and have this weird behavior, but don't worry about this. Once it reaches 0 and stays in 0 for a while, that's more than enough. And finally, the pattern for PACF of an ARMA model looks like an oscillating decay similar to the PACF from the MA model. So the ARMA model takes the ACF from the autoregressive component and the PACF from the moving average component. Now, to round our stuff up, let's recap the pattern so you guys can remember. Again, please don't worry about this line at all. The ACF of an autoregressive model starts at a point and it will decay and decay until it reaches 0. And the PACF will have a single cutoff point and then goes to 0. So if we notice something like this, like these ACFs and PACFs, we can be more than motivated to model this data using autoregressive components only. If we notice ACFs that have 1 or 2 cutoff points and PACFs that oscillate and decay towards 0, then we will be more motivated to use only moving average components. But when we notice that the ACF decays gradually and the PACF also decays and oscillating, then we might be better off modeling using ARMA. So that's the main goal for today, is to notice these pattern recognitions. I know that there are a lot of cases, like if this goes like this, maybe an AR, if this goes like this, an AR1, 2. I know that there's a lot of ifs. Don't worry about that at all. We will learn from next week onward how to get to an acceptable range of models and how to choose, what's the criteria to choose between the neighborhood of models. But that's all we have for today. Thank you so much for your attention. I will stop sharing now and upload the video. And I'll hang around, well, actually after 4 p.m. in case you have any questions or something. And yeah, thank you so much for today.